is why I have a great backup team to help me with this kind of thing. Yeah, so we'll record this so that we have this this online for people who couldn't make it. Yeah, as I said, Dr. Hirsch is relatively new to the university, although coming up on first year anniversary, I think. So that's amazing. I'll let her maybe spend 30 seconds just sort of talking a little bit about what she's doing at the university. But we're really, really glad, as many of you know, one of our original sponsors, into the university was John Percy about 20 years ago. And John is a longtime friend of the Toronto Centre of the RASC and has been at Arundel since it opened in the 60s. So he and Dr. Krill, who's I think on the call tonight on the meeting, sponsored the club to meet at Mississauga, at the University of Mississauga, Arundel, which is now University of Toronto, Mississauga. And so we have a long affiliation, and when John and John Percy and John Lester retired, they reached a point where they had to bring in some new people, and I'm so glad to introduce Dr. Lee Hirsch, who is an astronomer at the University of Toronto now, and Dan, you've got to keep muted there, please. Thank you. So we're so glad to welcome her as our speaker tonight. The talk is really interesting. This is Dr. Hirsch's the work that she's done for her doctorate, looking at the possibility of planets existing in multiple star systems, and of course that's why I promoted. I think she's promoted also the fact that if you look at Tatooine in Star Wars, that was a planet that was in a double star system. So the question is, can you in fact have planets in a stable system where there are two or more stars? And it's a great question, and I don't know how much supercomputer time you need to figure all this out, but it's a really interesting question, and I'm very, very pleased to introduce our speaker tonight, Dr. Lee Hirsch, and her talk, which is Here Come the Suns, the Statistics and Habitability of Planets in Binary Star Systems. Dr. Hirsch, it's all yours.
Awesome. Thank you so much, Randy. Okay, so as Randy mentioned, I'm sort of brand new here to the Toronto area, to Mississauga. I started as an assistant professor in this teaching stream at UTM in the fall. And so, yeah, this is my second semester teaching here, and I'm really happy to be with you all. And looking forward to sort of building a connection with the RASC. I guess it's pronounced RASC, I've learned tonight. Cool. So yeah, so I'll be talking about a topic that's sort of near and dear to my heart because it is what I studied as a graduate student and into my postdoc, and that is planets in binary star systems. So I kind of wanted to start out, and I always like to start out my talks with this little movie. It's a movie of a plot. Basically, it shows the evolution of the field of the discovery of exoplanets over time. So on the left, you see a plot showing planets' orbital periods and masses, and on the right, you see orbital periods and radii of those same planets. And each dot on this diagram shows you the position of a planet that we've discovered. The color of the dots indicates what method we used to find those planets. You'll see a lot of orange and blue dots here, and we'll talk about what those methods are in a little bit. But basically, the reason I like to start with this movie is because I feel like it gives a really good sense for the evolution of the field of exoplanets, kind of starting back in the 1990s, when the only planets we really knew about were the planets in our own solar system. And they sort of fill out this part of the diagram in the lower right-hand corner. And then starting in the mid-1990s with the discovery of 51 Pegasi b, there was just sort of this explosion of discovery. So when we talk about exoplanets, we're talking about a fairly young field, a field that's really only been going for about 30 years, but that has really undergone a huge change in those 30 years, from just finding and characterizing individual planets all the way up until now, when we have thousands of planets that we've discovered. And we can start to do really detailed statistics and try to learn some of the fundamental questions about how these planets are forming, how they are similar or different from the solar system, and sort of how common different types of planets are. Okay, so the big questions that we're trying to address as a field, as I mentioned, are sort of these questions about the formation of planets. How do we make planets? How does the universe make planets? And does it depend on the environments in which they're forming, or the metallicities of the systems? What factors go into determining what types of planets form and where? Part of this question is contextualizing our own solar system. So how common is the solar system? Are there other systems out there like our own system, or are we somewhat unique? And then how common is the Earth, right? Are there other habitable planets out there? Could there be inhabited planets in the long term? But for now, just these questions of, is there another Earth somewhere out there? And how common are planets like Earth? So we've learned quite a lot so far in just 30 years. We've gone from detecting a handful of planets and learning their detailed properties, to really having a large abundance of planets that we're able to statistically analyze and learn more about the population and the demographics of these planets. So one thing that we've learned so far is that habitable planets are likely fairly common, or at least planets similar in size and temperature to the Earth. So from the Kepler mission, we learned that if you picked out roughly 5 stars like the sun in the sky, roughly 3 of those stars would have a planet around the size of Earth in a roughly Earth-like temperature orbit. So it is very likely that habitable planets are abundant, at least to the best of our ability to understand whether a planet is habitable. We've also learned something about how common different planets of different sizes are. And in particular, we've learned that planets that are smaller than Neptune, but larger than Earth, these so-called super-Earths or sub-Neptunes, are by far the most common type of planet that is formed in the universe, or at least in the Milky Way. So planets like Jupiter and larger than that are much less common. Planets in between the size of Earth and Neptune seem to be sort of the dominant type of planet. And we don't have a planet like that in our own solar system. So this is kind of an interesting thing that we've learned. We don't really know exactly what these planets look like because we don't have a local example that we can go to and take detailed pictures. So we are sort of reliant on studying the statistics of these small planets that we've detected from afar with Kepler and trying to infer things about their properties. Another thing that we've learned is that planets in multi-planet systems tend to be similarly sized and regularly spaced. So if you have a multi-planet system, the planets in that system tend to be similar in size to one another, more similar in size to one another than they are to any random planet that you would pick out of your whole sample. And they are regularly spaced, which may be telling us something about the dynamics and the stability of these systems and their orbits. We've also learned that small planets fall into 2 distinct categories. So if you look at the distribution of planet sizes, we've found that there are some planets that are essentially super Earths, right? Rocky planets like the Earth, but a little bit scaled up, larger in size and mass, but without a significant atmosphere, sort of similar to the Earth, rocky planets. And then there are some planets that have these very thick hydrogen-helium atmospheres covering them, which we call sub-Neptunes. And this seems to be a signal of the way that planets are sculpted by the irradiation from their stars. So this is mainly true and has mainly been observed for planets close into their stars, where they are experiencing a great deal of irradiation from their stars, and this can end up sort of blowing off an entire atmosphere. So a planet might start out looking something like Neptune, and if its core is too low mass, its entire atmosphere would be lost, and it would sort of be converted into something that looks more like the Earth. And finally, one of the other sort of major things that we've learned so far, something that I've worked on and participated in myself, is studying the locations of giant planets and trying to understand where those giant planets tend to form in their solar systems. And we've found that the occurrence rate of giant planets takes a big step up, right around 1 astronomical unit, right around the distance between the Earth and the Sun, but around other stars. So giant planets seem to be very rare, interior to 1 astronomical unit within their systems, but fairly common. Something like 10% of systems probably has a giant planet outside of 1 AU. And this is also telling us something about the formation scenario for giant planets, something about the buildup of a core and the subsequent accretion of a gaseous envelope, which happens much more quickly in the exteriors of disks where volatile materials like water are in icy form rather than in gaseous form. So we've learned a lot in the last 30 years about planets, about their formation and their properties. But one thing I want to sort of highlight here, these are excerpts from feedback a lot. I think maybe somebody who is unmuted. Let's see. Oh, there we go. Thank you. So if we look in detail at some of the papers that were published with these particular results that I've shown you, I've highlighted some sections to read. So this one is by Bryson et al. 2020. This is the Kepler result on habitable planets. It says, we removed poorly characterized binary and evolved stars. This one from Weiss et al. Talks about the peas in a pod phenomenon, this similarly spaced and similarly separated planets. And it says, we discarded stars that were diluted by at least 5% by a second star in the Kepler aperture. And then finally, this one by Mayor et al., which says F and G stars with chromospheric activity index, high rotation stars have been rejected, as well as binaries. Okay, so these are just 3 examples, and I could show you plenty more examples of papers where they make these great discoveries and find these interesting trends about planets, and nearly every one of them will have a line like this that says, somewhere buried within the text, we threw out our binary systems. Okay, so the sort of common practice in the field of exoplanets is to remove binary stars from your planet surveys, right? Binary stars are systems where 2 stars are bound together. Some cases there are higher order multiple systems like triples or quadruple systems where even more than 2 stars are gravitationally bound to one another. And these are almost always thrown out of planet survey samples. So why is that the case? It turns out that a binary companion just makes it a lot harder for us to characterize and even to sometimes to find planets. And so we often reject these systems from our planet survey samples. So I'll show you sort of why that is first, and then I'll talk about why I think that's a problem. Okay, so let's think about how we actually find planets. One of the methods that we use is the transit method, where we're basically monitoring the brightness of a star over time, and we are measuring periodic dips in the brightness of the star as the planet crosses in front of the star. And so as the planet transits across the limb of the star, you would see this small dip, and then 1 period later, when the planet has gone all the way around, it will transit its star again. And so we measure a light curve that looks like this, and by measuring the depth of the transit, we can tell how much of the star's light was blocked out, and that tells us about the ratio between the planet's radius and the star's radius. Okay, so we can measure the transit depth, and if we know the radius of the star reasonably well, then we can determine the radius of the planet. what happens if there's a binary star system? Okay, so in the case of a single star system, this transit depth basically is a measure of the fraction of the star's light that gets blocked out. If there's a binary companion that we didn't know about, so an unresolved binary companion in the system, there's a little bit of extra light that we didn't account for. And as a result of there being this extra light that isn't blocked out during the transit looks a little bit shallower. So this makes us infer that the planet is smaller than it actually is, right? Because a shallower transit tells us that the planet is smaller, and if we don't know that there's a binary companion there, we don't have a way of correcting for the extra light from the binary companion. And this is an even worse effect if the planet is actually transiting the smaller of the two stars. Then it looks really tiny, and in fact can even be missed in surveys. So even though you have a relatively large planet that would otherwise have a reasonably deep transit that would be easy to detect, if there's an unknown binary companion there, you might actually not detect the planet at all. And if you do detect it, then its radius would be underestimated significantly. So this can pose problems both for finding planets, but also for understanding their occurrence rates, because when you calculate the occurrence rates of different types of planets, you have to sort your planets into bins. And if your planet radius is wrong, it will get sorted into the wrong bin. So you might overestimate the occurrence rate of these small planets because you think your big planets are actually small planets. On the other hand, you might underestimate the occurrence rate of the small planets because if there was already a small planet there, and the transit was diluted by a companion star, you probably didn't actually detect that planet at all. You probably missed it. So there are these sort of competing effects that overall kind of muddy the waters in terms of determining planet occurrence rates. Okay, and I'll point out that the transit missions that we have carried out thus far, the Kepler mission and the TESS mission, are low resolution missions, right? Their Kepler pixel was a 4 arcsecond by 4 arcsecond pixel. The TESS pixels are 20 arcseconds on a side. So most of the binary companions around nearby stars are not going to be resolved by either of these missions. And so it's very easy to miss these binary companions. Okay, I see there's a question. Let's see. Can you detect binary systems from the noise in the light levels? I'm not sure I understand that question, Alan. Maybe we can come back to that at the end. And then Rob asks, is there any evidence that the Earth had a big atmosphere in its early history? Okay, why don't we come back to these questions at the end, actually. Okay. So this sort of graphic is to show you what a typical sort of pixel might look like from Kepler. And if you take a higher resolution image of that field, you might see that there's actually 2 stars hiding behind your pixel. Okay, so the other method that we commonly use to find and characterize planets is called the radial velocity method. This one is a spectroscopic technique. So we look at the spectrum of a star. If the star has a planet orbiting around it, the star will actually do its own orbit around the center of mass of the system. And so both the planet and the star are moving. The planet is so faint that we don't see any light from it at all, but the star is moving, and as a result, the light of the star will be Doppler shifted towards the blue side of the spectrum when the star is coming towards us, and towards the red side of the spectrum when the star is moving away from us. And so we can monitor the time evolution of the wavelengths of the star's spectral lines and map out the orbit of the planet. So kind of like this, although this image, this graphic is greatly exaggerated, the variation in the wavelengths that we see from a planet orbiting around a star are at the 1,000th of a pixel level. So we're measuring very, very, very tiny changes in the wavelengths of these spectral lines. Okay, so how does a binary system complicate this picture? So here's what a stellar spectrum might look like. This is basically just mapping out brightness as a function of wavelength, where each of these dark bands corresponds to these dips that you're seeing in the spectrum. So let's imagine you actually have 2 stars. you can get what's called a double-lined spectroscopic binary. So a binary produces a spectrum that has two sets of spectral lines, one from each star. And because these two stars are in motion relative to one another, their lines are separated by a Doppler shift as well. The composite spectrum looks like this, right, if you add the two spectra together. So it's a lot more complicated than the spectrum of the single star. But it's even worse than that, right, because the two stars are in orbit around one another as well. And so they're Doppler shifting around their spectra due to the binary orbit, as well as the planetary orbit, if there was a planet orbiting one or both of these stars. And so not only do you have a double-lined spectrum due to your binary, the two sets of lines are sort of moving back and forth relative to one another. And it's incredibly complicated to disentangle the very tiny motions of a planet from these very large motions caused by the binary orbit. And so you can very easily miss planets in these types of systems as well from your radial velocity surveys. And so sort of the easiest thing that you can do is just reject any binary system from your planet search sample, right? And then you would get around this difficulty, and you would measure the occurrence rates of planets sort of undiluted by these more difficult systems. Unfortunately, I think that's a real problem. So binary systems are extremely common. We're not talking about throwing away 5% or 10% of our systems. For sun-like stars, these F, G, and K type stars that have masses and temperature similar to the sun, the fraction of stars with a companion is about 50%. So we're talking about half of the stars. More massive stars have even more stellar companions. Low mass stars have fewer stellar companions, but still a significant fraction. So when we throw away our binary systems, we are throwing out half of all of the stars in the sky. So we are really only studying the planets around half of the stars in the sky. We know a lot about binary systems as well. So we have extensively been studying binary systems since the 1800s, at least. People have been measuring out binary orbits. So we know a lot about them. We also know things like the sort of typical separation between binary stars in a given system. For sun-like stars, the most common separation between the stars is about 50 AU. That's sort of comparable to the outer edges of the solar system in our own system. And we also know the distribution of their masses. So for a sun-like primary star, roughly any companion mass from a tenth to one solar mass is approximately equally likely. So the binary companion could be an equal mass binary where both stars have the same mass. It could be a high mass ratio binary where one star is a sun-like star and one is a low mass M dwarf. We've also studied binarity for these low mass M dwarf type stars. They have fewer companions, but those companions tend to be closer in. So maybe a quarter, a little less than half of M dwarfs have a stellar companion. The most common separation between these binary companions is only 10 AU though, so that's comparable to Saturn's orbit. So you can see that the scale of the binary systems is typically pretty comparable to the scale of a planetary system, at least one like the solar system. So that's gonna affect things, right? If you have another star orbiting where Saturn is orbiting, that affects the solar system, or it would. So if we think about planets in binary star systems, there are sort of two configurations that you could imagine them having. There are the so-called circumbinary planets, where you have the binary stars in a small, tight orbit, and the planets orbiting around both of the stars all at once. This is the kind of planet that Tatooine would have been, as Randy mentioned, from Star Wars. And then there are circumstellar orbits. So if the binary is sufficiently widely separated, each individual star might have its own planetary system. And I will call these circumstellar orbits because the planets orbit around only a single star. And these ones I'll call circumbinary orbits, where the planets orbit around the whole binary. Okay, so we don't know all that much about circumbinary planets. They turn out to be really hard to find. We have found maybe of order 20 of these systems using the Kepler transit mission. You can see an example of what the light curve of a transiting circumbinary planet looks like. This is Kepler 16b. It's kind of like the poster child of circumbinary systems that we've actually discovered. And you can see the light curve of the Kepler 16 star system. There are these very deep transits. They're indicated in blue, and then the slightly shallower ones in yellow. These are actually due to eclipses of the stars on each other. So these are periods when the stars are eclipsing one another, the two stars. And then every now and then you see these green or red dips, which show when the planet eclipses one of the two stars or transits one of the two stars. So there's like a slightly deeper dip for when the planet transits star A, and a slightly shallower dip when the planet transits star B. Okay, so it's hard to find these with our algorithms because these transits tend not to be as periodic as they are around a single star system. The stars are moving, so the position that they're in when the planet transits is not always exactly the same. So that breaks some of the periodicity. So it's a lot harder to find these systems. One thing that we have sort of learned is that of all of the sort of circumbinary planets that we've been able to find, they sort of pile up near the very edge of stability. So if a planet orbits too close to the binary system, it will actually be destabilized by torques from the moving masses at the center of the system. So there's sort of a threshold interior to which the planet would be destabilized. And almost all of the circumbinary planets that we found are very close, but just outside of that stability region. So that's kind of interesting. We do know about a larger sample of circumstellar planets in binary star systems. So here's just a handful of those. You can see sort of a little graphic here that shows you the location. So the primary star would be at 0 here, over on the left-hand side. The blue dot indicates the location of the planet, and then the yellow dot out here shows you where the stellar companion is located. And then these black vertical bars show you likewise a stability threshold, right? So for circumstellar orbits, the planets are stable when they're very close to one of the stars, but the farther away they get from their own host star, the more likely they are to be destabilized. And you can see that none of these fall outside of that stability regime, as we indeed probably wouldn't expect them to. So this is sort of the context with which I wanted to try to understand if we could actually say something about the occurrence rates. How common are planets in these circumstellar orbits around sun-like stars in binary systems, right? So I wanted to see if we could go out and actually measure this, despite the fact that the binary companion makes it harder to find and characterize planets. So this is sort of the question that I wanted to ask. There's some more sort of theory that gives us some indications of what we might expect to learn. So for example, in single star systems, the protoplanetary disk out of which planets form are typically around 100 astronomical units in size. In binary systems, we expect that interactions between the binary companion and the protoplanetary disk would disrupt these disks and make them smaller. They would truncate the disks around each star. So there would be less material to form the planets, and also they would last for less time, right? These disks would be shorter lived. Let's see. So I see a question from Shreya asking what would have happened to a planet orbiting in the instability region? And I'll talk a little bit more about that in this slide. But basically what would happen is that it would interact with the binary and be destabilized. So it would be essentially either ejected from the system or it would be sent spiraling into one of the stars. And so we would expect those planets to be short-lived. They would not survive in those regions for very long. This schematic sort of maps out the stability region in a binary system. And when we're talking about circumstellar orbits, planets are only stable within maybe like a third of the binary separation, so out to a third of the distance to the second star. And if they formed out further out here, they would then be either ejected from the system, or their orbits would be perturbed. So they would not stay on those types of orbits. And likewise for circumbinary planets, stability is limited to orbits outside of around 3-ish times the binary separation, right? So the two companion stars are in here, then 3 times the binary separation is roughly the limit outside of which planets could survive, but interior to which they would again be interacting with the stellar companion and being destabilized, being ejected from the system. Okay. So here's what we did. Here's our sort of observational survey. We chose a sample of all of the sun-like stars within 25 parsecs of us in the Northern Hemisphere. It's roughly 300 stars. And then we observed all of these 300 stars with 2 methods. One was with adaptive optics imaging, so high resolution imaging. This allows us to distinguish which stars have companions and which ones are single stars. And then we used radial velocity, spectroscopic data, to obtain radial velocities for each of these 300 stars as well. So in some cases, we were able to also identify stars as binaries based on their radial velocity data, as they had these very large variations due to the binary orbit. But we did our best to also measure whether those stars could have hosted planets. And beyond just finding planets with these radial velocity data, we were also able to use the data to get a very accurate calibration for what planets we could have found in these systems and what planets we could not have found in these systems. So we could set limits in terms of our sensitivity to planets for each of the individual 300 stars in our sample, regardless of whether they were binaries or single star systems. So this allows us to calculate occurrence rates to basically measure how common planets are. And we could focus on regimes of planetary properties where we actually had great sensitivity to the planets, and try to say something about the relative occurrence rates of planets in the single star systems as compared to the binary star systems. Okay, so here's just a little graphic. This is the Lick Observatory in California. That's Keck Observatory on Mauna Kea. We use data from all of these various telescopes on this sample of stars, which are basically sun-like stars, so stars with masses pretty comparable to that of the sun, that were within 25 parsecs, so a volume-limited sample. And here's sort of the results that we found. So how to interpret this plot is sort of to read off on the left for each of these samples the occurrence rate. So for the single star systems, we found an occurrence rate of about 18%, so roughly 18% of stars has a planet in our regime of sensitivity for the single star systems. And then the width of this sort of loop-de-loop thing here tells you how certain we are, right? So how precisely we are measuring this occurrence rate. So for the single star systems, we measure an occurrence rate for planets of around 18 planets per 100 stars. If we zoom in on the close binary systems, so these are binary systems where the companions are closer than 100 AU to one another, you can see that the occurrence rate of the planets is a lot lower, right? Only like 4%. So only 4 planets per 100 stars. So that's significantly lower. And even with the sort of uncertainties on these measurements, this is a significant result. So this is telling us that there are far fewer planets, at least giant planets that we were sensitive to, in these close binary systems than there are in single star systems. Okay. In contrast, if you look at the wide binary systems, these are binary systems where the two stars are at least 100 AU apart. They don't have a significant difference in occurrence rates compared to the single star systems. So, 18 planets per 100 star, as opposed to 20 planets per 100 star. It's not a significant difference, especially considering the fairly large error bars here. But also keep in mind that we were only measuring the occurrence rates for the primary star, so the more massive star in each of these binary systems. There's still a second star in those systems that might itself host planets. So if you assume that even the lower mass star can host planets, then these wide binary systems should host more planets than the single star systems, just by nature of having more host stars. Okay, so this was sort of the primary result, showing us that these binary companions are likely having an inhibiting effect on the formation or stability of planets if they are closely separated. But if they are widely separated, more than 100 AU, they're probably not having much of an inhibitive effect on the formation of planets. And so this is telling us something about sort of the threshold interior to which a binary companion really screws up this whole process of planet formation, but exterior to which it doesn't seem to have this serious effect. What it does seem to do potentially is change where the planets are located. So in the single star systems, if we break up our occurrence rates and we measure how many planets per star there are between 0.1 and 1 AU, so these are very close-in planets, interior to where Earth is located, the number is pretty small, only 3%. But exterior to 1 AU, between 1 and 10 AU, the number gets a lot higher, 18%, right? So this is comparable to the result I showed you for single star systems at the very beginning, that it seems like giant planets have a large jump up in occurrence rate outside of 1 AU. So it's good that we're measuring this same result for our sample of single star systems. They should be comparable to the single star systems that were observed for this result. But if you compare that in the wide binary systems, we don't see that same trend, right? Rather, there's sort of the same number of planets that are close to their star as there are that are farther away from their star. So our thought is that perhaps this might indicate something to do with a wide binary causing planetary migration. So maybe the giant planets are forming out here beyond 1 AU, but via interactions with their binary companion, they're actually migrating inward. Now, this is a theory that has been proposed before to explain the formation of hot Jupiter planets. These were the very first planets to ever be discovered. There are these Jupiter-like planets that are located on orbital periods of only 3 days. They're very close to their stars. They're extremely hot, and it's hard to explain how they get there. And one of the ways that has been proposed for how they get there is via these interactions with an outer binary companion. And so perhaps what we're seeing is sort of evidence of this, what's called Kozai-Vlitov migration mechanism, where the outer binary companion interacts with the giant planet and causes the giant planet orbit to shrink, essentially. Okay. So I will mention that this study was really only sensitive to giant planets. We weren't able to detect Earth-like or rocky planets, just based on the sensitivity of our measurements, especially in the binary star systems. But that doesn't necessarily, make it invalid when we're thinking about the occurrence rates of Earth-like planets, because the presence of giant planets almost certainly affects the formation and the properties of inner terrestrial planets in a given system. So, Jupiter had a large impact in the early evolution of the solar system. So giant planets can affect the stability of terrestrial planet orbits and asteroids. It can cause bombardment, which might contribute to water delivery, but might also contribute to atmospheric loss for the inner sort of rocky planets in a system. And they can also affect the disk mass that's available to form into small planets. So there is definitely a connection, although not one that has been really accurately quantified, between what's going on with the outer giant planets and what's going on with the inner rocky planets. Okay. So for the last like 10 minutes or so of my talk here, I wanted to think a little bit about what planets in binary systems might be like if they are able to form. So here's a picture of Tatooine, right? So this is our science fiction based concept of what a circumbinary planet might be like. This is one of my favorite examples. So this is from 2013. It's kind of an old example, but there's this this like sort of tradition of writing fun spoof papers for April Fool's Day in the astronomy community. And so people will put a great deal of effort into writing these like really fun kind of wacky papers for April Fool's Day. And this one was one of my favorites from 2013. It basically proposed that the odd seasonal changes in the George R.R. Martin's what's it called? Game of Thrones series could be explained if the planet orbited a binary system, and that caused sort of these variations to its length of its seasons. So that's why winter is always coming, and sometimes they have these sort of global winters. But really, sort of one of the main kind of issues in terms of thinking about what planets and binary stars might be like is a sort of a competition between stability and habitability, right? So we already talked a little bit about what stability means, the fact that in a binary system, certain regions, like certain orbits, just aren't stable. They would interact with the binary companion and be ejected. So for the circumstellar planets, they have to be sufficiently close to their host star. For the circumbinary planets, they have to be sufficiently far away from the binary system in order to avoid being destabilized. There's also this sort of competing effect when we're trying to think about like living on a planet in a binary system, where the temperature has to be right in order for them to be habitable, right? They have to be in the so-called Goldilocks zone, or the habitable zone, where they're far enough away from their star that the temperatures are comfortable for liquid water, right? Liquid water must be able to exist on the surface for life as we know it to exist. And in some cases, these two competing requirements, stability and habitability, might mean that you could never even get a habitable planet around one of these binary systems at all. So for example, in this upper right-hand corner, here's an example of a binary system where the only stable orbits are within the red dashed line close to the star. But the only habitable orbits are in the gray shaded region, so outside of that stability region. So in a system like this, any stable planet would be way too hot for life, whereas any habitable planet would quickly be destabilized. And so that might like strongly prevent there from being a habitable planet in this system. And likewise, here's an example of a circumbinary system where a similar thing is true. Down here on the left, you can see an example of a system where all the stable orbits are out here beyond the red dashed line, and the habitable orbits are interior to that. And so again, you wouldn't be able to get a habitable planet on this in this system because it would quickly be destabilized. Okay, so I just wanted to sort of summarize everything that we've talked about, which is that the field of exoplanets has evolved a great deal since its beginning 3 decades ago and the first planet discoveries in the mid-1990s until today. We know of thousands of planets. We're really studying the statistics of these planets. But one population that really needs more study is these binary systems. They comprise half of all stars in the sky, roughly. So we're not talking about a small sample. We're talking about a major potential environment for planet formation. We think that the close binaries will strongly inhibit planet formation. But the wide binaries are really interesting because they probably don't prevent giant planets from forming, but they may cause giant planets to migrate, which may then trickle down in terms of the effects on potentially habitable rocky planets in those same systems. Okay, Cool. So I'm happy to take questions now, and I see there's a whole bunch of questions in the chat. Should I go ahead and go through these? I would have to scroll back up, or Randy, do you typically moderate?
When he's not sleeping.
Okay, I can start going through questions. Maybe I'll just start where I'm at and then scroll upwards instead, if that's okay with everybody.
Sorry, I was distracted there by some alien source.
No worries.
Not my wife. Yeah, do you want to go through the chat there?
Sure, sounds good.
Okay.
Let's see, I'm just going to start here with Don's question. So mentioned early in the talk that the most commonly found planets are super-Earths to Neptune-sized. Does this reflect that smaller planets like Mars, Venus, and Mercury are comparatively rare, or existing equipment cannot yet detect these? Yeah, that's a great question. And I think it's probably most likely the detection bias that we're seeing here. We are much less sensitive to planets smaller than Earth, and therefore we're not able to very accurately characterize how common they are in many cases. And there's not really any indication of a turnover in terms of the occurrence rates. As you go to smaller and smaller planet sizes, it's just that we have much less leverage at those small sizes. So I think that's mostly an observational effect. Okay, I've realized that there's an issue with my approach of starting at the bottom and going up, which is that new questions are going to appear. So I'm going to go back up instead.
Do you want me to feed them to you?
Sure, or I can just scroll here.
Okay.
So all the way back at the beginning, I see Alan's question: can you detect binary systems from the noise in the light levels? So I think you were looking at the light curves that I was plotting, and I don't think that you would be able to determine if a system is a binary from the noise in the light levels. Those were more illustrative plots rather than actual data from a particular binary system. All stars have a certain amount of variability, and that varies a lot as a function of things like stellar age and stellar type, but I don't think the binary would significantly affect that. From Rob, is there any evidence that the Earth had a big atmosphere in its early history and were the core of a mini Neptune? So I think the answer to that is no. That process by which these large atmospheres are sculpted away by the incident radiation from the star mostly happens in the inner parts of solar systems, like where the planets are very close to their stars. So that's mainly an effect that we've seen for planets with orbits less than 50 days or 100 days. So when you get out far enough away from the star to 1 AU where the Earth is located, that sort of sculpting doesn't really happen nearly as much. But we also have much less information about the planets orbiting in those locations. So it's a lot harder to say whether that bimodal distribution continues out to those orbits. Okay, from Chris, is the orbit of a circumbinary planet usually in the same plane as the orbit of the stars? That's a great question. I'm not sure we know, because we don't have enough circumbinary systems, but I think the answer is probably that not necessarily. It wouldn't necessarily be in the same plane as the orbit of the binary. And depending on sort of the relative mutual inclinations, different gravitational effects can actually happen. So for example, that Kozai-Lidov effect that I was talking about before, although that's a different configuration, that's an effect that happens for circumstellar planets, that requires the inclinations of the planet and the star to be quite different from one another in order to occur. Okay, so from Alan, presumably you could have a planet at a Lagrange point in a circumstellar system. Could it be stable enough to last? Yeah, I get asked about Lagrange points a lot, I think, when I talk about circumbinary and circumstellar planetary systems. I'm just not sure how you form a planet at a Lagrange point. So I'm not sure if you would end up with a planet, like it is a stable region, but I don't know how you make a planet there. Like you would have to get really lucky to have a planet form right at that location and not just slightly out of that location and not survive. It's an interesting question, yeah. I think I addressed Shreya's question already, so then I'll skip that to Randy's. So some science fiction stories postulate an outer planet, Jupiter, becoming a star. Is that theoretically possible? I think I remember, isn't that like in 2001: A Space Odyssey, that series that's at least one series that I can think of that I've read where that happens.
I think it's an Isaac Asimov story, but you know.
Oh, okay. Yeah, I don't know how does the planet become a star though? You would need to infuse it with a huge amount of mass, right?
Yes.
Jupiter is 1,000 times less massive than the sun, and even the most low mass stars are 80 Jupiter masses or more. So you'd have to increase the mass of Jupiter by a whole lot to start fusion. And I don't know where that mass comes from. Aliens, I guess.
I guess I was kind of wondering if you can have a central star and then some planets and then maybe an external rotating star outside of them. Or is it all...
like what would the light conditions be like on a planet in a circumstellar orbit in a binary system?
I mean, they'd be all messed up, but could you theoretically have that amount of mass outside, that far away from the central star to do something like that?
To make a planet into a star, you mean?
Well, just to form a star in the first place, I guess.
Oh, well, so yeah, I guess that's an interesting question. So we think that the binary stars will probably form at the same time. Like they form out of fragmentation of the original cloud of gas and dust that is forming into the stars. What you're describing is kind of like one of the mechanisms we think giant planets may form in. So basically it's sort of like if you have a disk of material, could you undergo some instability and collapse the disk down and actually form a massive enough object that it would be a star?
Yeah.
And I don't think disks have enough mass in them.
So they're more, the mass is mainly concentrated at the center.
Exactly, yeah. So the sun is like 99.8% the mass of the solar system or something like that. I can't remember what the exact number is, but yeah, I don't think there's enough mass in a disk to like gravitationally instability form into a star.
That makes sense.
Yeah, cool. So Rob's question, is it possible to have a stable orbit where the planet orbits both stars in some sort of figure 8 configuration? I don't think so. Yeah, I don't think so, but I don't know. There's a good the three body problem. I don't know if anyone has read the three body problem. It's a great science fiction novel where they put a planet in the Alpha Centauri system and it does that sort of thing, right? It keeps getting like captured by one or the other of the stars. I don't know if that's really, I don't think that's really believable. I think that planet wouldn't last long term. It would probably be ejected from the system rather than just being, constantly being transferred between the various stars. But it was a cool book. Let's see. So Blake asked, did you find triples or quadruple stellar systems with planets? We did find triple and quadruple stellar systems. I can't remember. I can't remember if any of them hosted the planets. I want to say probably not very many, if few. But that's a great question. Okay, so I think I answered Don's question. Then Giselle's question: do binary stars have an equal mass and size from one another? Can a smaller binary star almost be considered as sort of like a moon to another star? So they often do not have the same size or mass. So there are binary systems that all have a range of different stellar masses for their companions. So there are equal mass binaries where both stars are the same mass, but there are also plenty of systems where the companion is much lower in mass. Even if you go all the way down into the brown dwarf regime, right? There are systems where you have a star with a brown dwarf companion as well. Although those seem to be less common than actual binary star systems. But if you sort of map out the distribution of companion masses, it's relatively flat. So you're equally likely to get a 0.1 solar mass star as a companion versus a 0.5 solar mass star versus a 1 solar mass star. So they follow this sort of broad distribution. Okay, Yassine's question, can there be habitable planets around systems where white dwarfs orbit the bigger stars or X-ray binaries? Oh, that's a really interesting question. So not all that long ago, we've sort of started to discover a handful of planets around white dwarfs. It turns out because white dwarfs are really tiny, if you look for these systems in transit missions, you can actually have complete transits, right? White dwarfs are around the same size as the planet Earth is. So if you have a giant planet orbiting a white dwarf, it could actually completely block the star out. And even, like very recently, a few of these systems have been discovered. I don't know about, there are certainly also binary systems where you have one component as a white dwarf, right? These are systems where one star would have evolved off the main sequence and turned into a white dwarf. So what used to be the primary star in the system is now the white dwarf companion. It's much fainter. So there could, like, if the two stars are far enough apart, I think there could still be planets orbiting the stellar component of those systems. I don't think we found anything like that within 25 parsecs of the sun. You might have to go out farther than that to a larger volume to get something that sort of unique. But yeah, I think that could be possible. Okay, Ron is asking, I would think planets would remove angular momentum from two stars quickly going around each other. Is it possible the sun had a twin which eventually fell into it? Would the planet remove angular momentum? I don't think the planet would remove angular momentum, at least unless it was destabilized, right? So if you have the planet in a stable orbit exterior to the stability zone of a circumbinary, I don't see any reason why it would like quickly remove angular momentum. I don't think the sun had a twin which eventually fell into it. Yeah, I don't think that's the case. I'm sure we could rule that out. Yeah, it's an interesting scenario. Okay, so Ali asked, do I foresee some time of Webb telescope being allocated for the study of binary systems? Oh, that's an interesting question. It depends a lot on what people propose to do with Webb, I think. I don't think there's any like guaranteed time dedicated to binary systems, although there certainly is for imaging planets around some of those nearby stars that are included in my sample. But maybe eventually, hopefully. And I don't think it would make too much of a difference as long as it was a widely enough separated binary companion to imaging with Webb. Let's see. Am I considering revisiting as instruments improve? Can we more easily detect sub-Earth worlds? That's a great question. So with radial velocities, instruments are indeed improving. A new generation of instruments is being developed and commissioned. But part of sort of the difficulty in observing an Earth-like planet with the radial velocity method is actually intrinsic noise from the star itself. And that is an area that we are still very actively working on, but at the moment, it's kind of the tallest tentpole in terms of reaching the precision levels we would need to find an Earth-like planet orbiting a sun-like star with the radial velocity method. Basically, the stars are too noisy. And you need to really deeply understand stellar activity, so the stellar magnetic cycle and the spot coverage on the surface of the star over time in order to fit it away and achieve the precisions you need to find Earth-like planets. So that is sort of an area of very active ongoing research, trying to eventually reach the point where we can find the Earth. At this point, I think that is a larger challenge than the technological challenge. Like the new instruments are capable, they're high enough resolution to measure the signal of an Earth-like planet, but we have to be able to remove the contribution from the stellar noise before we'll be able to do that. And that is regardless of whether you're in a single or a binary star system. Okay, let's see. We hear of lone drifter planets in the news sometimes. Would these planets be examples of ejected planets, and how do we detect them? Yeah, very possibly. So you hear about these rogue planets sometimes. So these could be objects that form like stars, like kind of the tail end of brown dwarfs. But they could also equally be something like, you know, a planet that was ejected from its host star system and is now sort of roaming through space freely. Actually, I talked to someone recently who works on interstellar asteroids, like the Oumuamua object, the interstellar comet that flew through our system, who was thinking about whether binary stars would be particularly good at producing these kind of interstellar comets and asteroids, like very good at ejecting its small rocky bodies. So that's another thing that we could think about in terms of these, you know, finding these ejected bodies from destabilization via a binary interaction. Yeah, Chris, that's what I was thinking of in the 2001: A Space Odyssey series.
Yeah, the second book is actually 2010 Odyssey.
Yes.
Right? I put the wrong year. Sorry about that.
Got it. Yeah, it's been a little while since I read those, but I remember that happening. Okay, so Keith's question: white dwarf planetary systems, are there issues about how the planets or planetary materials survive the formation of the white dwarf? Yeah, so that's a really good question. In some cases, I think we consider those to be somewhat of second generation planets, like maybe the planet was destroyed when the white dwarf formed, right? The star would have gone through this giant phase where it expanded out to the orbit of Earth, or even farther than that, depending on the star's mass. So it could have engulfed and eaten planets that were orbiting around it originally. So perhaps what we're seeing is then the reformation, like a second generation of planets, especially if they're orbiting relatively close in. They probably weren't there during the giant phase. They may have sort of formed out of the material left over after the formation of the white dwarf. Okay, Yassine asks, can planets orbit to neutron stars? Ooh, I don't know. Could they be habitable? That's a hard question to answer. I mean, we can't even say whether planets orbiting other sun-like stars are habitable, so I would be very hard-pressed to say whether a planet orbiting a neutron star could be habitable. But whether a planet could orbit neutron stars, I don't see why not, as long as they were sufficiently far away from the stars. Let's see. How do you separate Earth-sized sunspots on a star from Earth-sized planets transiting it? Someone in my class asked me this same question like 2 days ago, actually. So it has to do with how long the star spot versus the planet would be covering the surface of the star and causing this dip in brightness, right? A star spot would be visible on the face of the star for half of the star's rotation period. So for the sun, that's 20 days. So a sunspot would be on the surface of the sun for 10 days. A planet transiting across a star, transits are usually only an hour or two, a few hours in length. And then there's a long time as the planet makes the rest of its orbit between the subsequent transits. So for a sunspot, you would see a 10-hour dip and then a 10-hour peak, and then a 10-hour dip and then a 10-hour peak. For a planet, you would see a few hour-long, 10-day dip and 10-day peak. The sun's rotation rate is 20 days, not 20 hours. But a transit of a planet would be like a few hours long, and then it might be days until the next transit comes around. So that it distinguishes those two signatures. Okay, so Fred's asking, do you use off-the-shelf algorithms or create your own to parse out the data you desire? So a large part of the project that I did was writing algorithms to find planets within our RB data, and then also to estimate our sensitivity to planets. So writing the algorithms that will automatically search for planets. And then once you have sort of an automated search pipeline, you can inject fake planets into your data and then try to recover them with your pipeline. And that tells you how capable you are of finding planets of different masses and orbital periods. So that's the algorithm that we tend to use when we're trying to estimate our sensitivity to planets in a particular data set. Is we model a fake planet, we inject it into our data, and we see if our algorithm can recover it. And we do that for all different planet periods and all different planet masses. Then we can sort of map out in terms of planet sizes and orbits where we're sensitive to planets and where we're not, based on which injected planets we can recover and which we can't. And so, yeah, I worked a lot on writing algorithms to do that sort of thing with our data. Dan's question, Earth's water largely came from comet and asteroid collisions. Are these events less likely to occur in binary systems, making it less likely that there are water-rich worlds in binary systems? So I think actually, we don't know for sure, right? There's almost certainly some correlation in terms of, a binary companion might actually increase the rate of bombardment. Jupiter had a strong impact on the bombardment of the inner solar system planets. So maybe a stellar companion would also have a similar effect. But it's hard to parse out exactly what that effect would be. That would be a very complicated numerical model and probably highly dependent on where you put your planets and all the masses of the various particles involved. And so that would be hard. Let's see, Fred is asking, how do you manage all the data? For this scale of survey is actually not that unreasonable. That's going to be a major challenge in the whole astronomical field in the coming decades, I think, is data management, because we're starting these surveys that are going to just produce these incredible amounts of data that, at some point you can't put human eyes on all of that data. We're already in that regime for some surveys and some instruments and some telescopes. And I think we're moving even more in that direction. So in that case, things like machine learning or AI algorithms can come in. That's not something I've personally worked on in the past, but I think it's definitely a direction the field's gonna need to go in more and more in the future. Let's see, how likely it is it, the sun, as far as we know, does not have a binary companion. Am I planning to use citizen scientists? I don't have specific plans for citizen science, but it would be something that would be really interesting to think about. I don't have the data volumes that would require it personally. So yeah, but I do really admire a lot of the citizen science projects that have been done. I had my students read about the Galaxy Zoo recently, and they're gonna do some galaxy classifications for their homework next week.
The Galaxy Zoo?
Yeah, the Galaxy Zoo.
Yeah.
Mm-hmm. I think that's. Oh wait, there's more questions.
Oh no, well that's okay. That's just down.
Okay. No worries. Mercy, the end of the use of these methods is satellite in ooh. Oh, I hope not.
We're going to have a talk in a few months about that, actually. Astronomer from the University of Regina.
Cool.
Yeah, it's a real problem. Lee, thank you very much. This has been really interesting. I think the interesting questions that have been generated from your talk have been quite interesting. So thank you very much for talking to us tonight and bringing your expertise. And one thing I like to ask of people who are working on certain projects is that what do you hope to not achieve, but what areas do you hope to sort of look at in the next 5 years? Mm-hmm. Now that you are where you are and what you know. What areas do you want to focus on in the next 5 years?
That's a great question. So one thing I'm interested in sort of pursuing is we've done all this work to observe the primary sun-like stars in all of these binary systems in the solar neighborhood, but we don't have nearly as much data on their stellar companions. Part of that is that they're fainter and they're harder to observe, but I think it would be really interesting to also study the companions, because we're thinking about the scenario here of a planet orbiting the most massive star in the system, and maybe there's a low mass stellar companion to perturb it. any effect would be even stronger, I think, when we're thinking about a low mass star with a very high mass stellar companion perturbing its planets. So that might tell us something. And the other thing is to push to smaller masses, right, and longer orbital periods. So with continued monitoring of these stars, we can get longer data sets that allow us to push to longer planet orbits. And with higher precision data, we can push to smaller planet masses. So to just try to continue to probe the sort of outer parts of these solar systems, the lower mass planets in these systems, and try to continue to sort of extend our understanding of how multiplicity affects planet formation, not just for the close-in giant planets, but also for the lower mass planets, the Earth-like planets, or the more distant giant planets in these systems.
So that sounds great. It just doesn't seem all that long ago that we were hearing about the first confirmation of extrasolar planets, period.
Yeah, it's a very, right, that's part of why I like to show that video. It's a young field, and I feel like we've made great strides. So I'm eager to see where we go next.
Great. Well, we'll look forward to not only following your research, but also hopefully having you out for a meeting.
That would be fantastic.
University, one of these days, hopefully before the summer, but we'll definitely have you out and get some face-to-face time. Thank you very much, Dr. Hirsch, for a really, really interesting talk. It's a fascinating area of research, and we appreciate you sharing it with us tonight.
Thank you very much, and thank you all for coming.
Thank you. Not much more to talk about our future meetings. We have a February 11th potpourri meeting, which is just our general series of short talks from members. And on the 25th of February, we're working towards our annual meeting to look back at 2021. The newsletter messenger went out today, so members should receive a notification in the mail. And we'll be looking at the activities of our second year under COVID situation, but we'll talk about our finances and our what things we did last year and our plans for 2022. And hopefully by summertime, we'll be able to get back to Riverwood for some public outreach and hopefully get a little bit of normalcy. But as I say, in my president's message, I predicted last spring that things would be more or less back to normal by Labor Day, and of course that was not a good prediction. So I will leave it at that. So I don't think there a lot of thank yous, Dr. Hirsch, in the chat. So we appreciate very much your time tonight, and wish everyone be safe, get your booster, clear skies, cold skies. But we'll see you in a couple of weeks. And again, hello and welcome, and thank you for attending, all our friends from across the country tonight. So good night to all of our RASE friends.
Thank you.
Good night.